Today I want to spend a few minutes talking about how quickly these nuclear decay equations take place, or how quickly radioactivity takes place. So I need to define a term called half-life, though. Half-life is going to be the time that it takes, forget about this word for a second, we'll come back to that, for half of a radioactive sample to decay. For instance, let's say you have a radioactive element X. The half-life of radioactive element X, the symbol for half-life, by the way, is T1/2. The half-life is 5 years. If you have 1 kilogram of radioactive element X to start off, then after 5 years, you will have half of a kilogram of radioactive element X. After 5 years, 1 half-life, the time that it takes for half of a sample to decay, half of it will remain. You'll be left with 500 grams. Now, that doesn't mean the other 500 grams is decayed to nothing. It's decayed into some other element, right? If you have carbon-14, it decays into nitrogen-14 and a beta particle. Okay? Element X might decay into element Y and an alpha particle. But after 1 half-life, after 5 years in this case, half of that will have decayed. In other words, you'll only have 500 grams of element X left. After 2 half-lives, how much do you think you're going to have left? Is it all going to be gone now? After 1 half-life, you're down to 500 grams. After 2 half-lives, you're down to 250 grams, because you always lose half of what you started with in that half-life. Now, why is that the case? Why does half of it decay in 5 years or half of it decay in 1 half-life? Because each nucleus, each individual nucleus has a 50% chance of decaying during that half-life. It's kind of like flipping coins. If you have 1,000 coins and you flip them all, each one of them has a 50% chance of landing on heads. Agree? Each one of them has exactly a 50% chance of landing on heads. So, on average, how many heads are we going to have after flipping them all once? 50% of them, 500 of them, right? Now, it might not necessarily be exactly 50%, right? Each one of them has a 50% chance of being heads, which means on average, you'll end up with 500 that will be heads. Statistically, it'll be 50-50 because of that 50% chance of each one of them becoming heads. Well, that's the deal with half-life as well. In 5 years, each element, each nucleus of element X has a 50% chance of decaying. That means on average, or statistically, 500 grams will be left after 1 half-life. Could be 501, could be 499. Statistically, though, it's going to be 500. Now, am I just simplifying things for you? Because you guys aren't smart enough to understand the real deal? Not at all. If you guys go on and take a course in physics, you will not learn any more certainty than I'm teaching you today with this. It is possible when you flip 1,000 coins that all of them will end up heads, right? But that's incredibly unlikely. You could figure out the probability of that. It would be astronomical. It would be possible. Statistically, 50% of them will end up heads. When you have a 1,000, let's say, nuclei of element X, because each one of them has a 50% chance of decaying, statistically, you'll end up with 500 heads. Sorry, 500 that have decayed and 500 that haven't decayed. We can't do any better than that. We can't do any better than statistics because each one has a 50% chance of decaying. You can't predict with any more certainty what the percentage that remains after 1 half-life will be than you can predict how many coins will be left after flipping them all once. It's a statistical probability. It's the best you can do. But if you have a big enough sample size, statistics usually work, right? It usually works. If you flip 2 coins, all bets are off, right? How many are going to be heads? But if you flip 1,000, it's going to be pretty close to 50-50. The law of averages tends to take hold once you have enough elements decaying or enough nuclei decaying. All right, let me give you two equations. One equation that does not appear in your data sheet, and one equation that does. Here's the first one. N is equal to T over T1/2. N stands for the number of half-lives. If the half-life of radioactive element X is 5 years, and 15 years have gone by, that's 3 half-lives. T stands for the time that's elapsed. That would be the 15 years in that example that I just gave you. And T1/2 stands for the half-life. That would be the 5 years in the example that I just gave you. So 15 divided by 5, the time divided by the half-life, gives me 3. The number of half-lives is 3. That equation is not provided for in your data sheet because it's kind of intuitive, right? You want to find out how many half-lives have gone by, just divide the time by the half-life. It's logical. You don't really need an equation for that. The other one, yeah, it's on your data sheet, and it's good that it is because you definitely need an equation for this one. Many of you will recognize this equation. Many of you have seen one form of this equation before in math class. Big N is equal to big N0 times 1/2 to the little n. How many people recognize that in some form or another? That's your your exponential decay equation, right? If you wanted to change it to exponential growth, what would you do? Yeah, your 1/2 wouldn't be 1/2, right? It would be like a 2, or it could be something else, right? But it wouldn't be a half. It wouldn't be a fraction, right? I suppose it could be an improper fraction, like a 4/2 kind of thing, right? But not a number that's smaller than 1. Definitely not a number that's smaller than 1. If it's bigger than 1, it's growth. If it's smaller than 1, it's decay, right? You end up with less than what you started with. Let's identify some of the variables here. N, of course, little n stands for the number of half-lives, which we may have given to us. We may have to solve for using the equation that's on the left-hand side. The number of half-lives. N0 is the initial amount. This is what we start with. N is the final amount. This is what we end up with. Now, here's kind of a wacky thing. The initial amount and the final amount, as long as it's consistent, you measure them both in the same units, you can measure whatever units you want. Maybe grams, maybe kilograms, maybe just a number. I have 28 grams of carbon-14. I have 613,000 nuclei in carbon-14. Or maybe it's percent. What percent remains after 5 years? How much percentage of the initial amount remains after 5 years? Maybe it's decays per second. How many decays per second take place after 6 years? Maybe it's a unit called the becquerel, BQ, which you don't really have to be familiar with that. It indicates an amount. It's the rate of decay, how many decays per second that take place. Here's the point that I want to make with this. Even if you see a unit like this that you don't recognize, that's okay. A number that you get in one of these questions is either going to be time, right, T or T1/2, in which case you should recognize it, right? If it's in days, years, seconds, hours, minutes, centuries, decades, millennia, you should recognize if it's time, T or T1/2. If it's not time, it's N and N0. Even if it's a unit you don't recognize like this, becquerel, it's got to be N and N0 if it's not T, if it's not time, right? I'm going to highlight this one because this one does appear on our data sheet. I'm going to star this one because this one does not appear on our data sheet. And you're going to want to be able to use both of those. We're going to do 2 examples with you right now, and then we're going to give you a bit of a break. Come back and work on some problems, and then we'll do one more example with you a little bit later in class, and then that'll be it. Here's the first one that's on the handout that I gave you the first day of this unit. It says the half-life of hydrogen-7 is 2.3 times 10 to the minus 23 seconds. Talk about a quick rate of decay. How much of a 27-gram sample of hydrogen-7 would remain after 1.84 times 10 to the negative 22 seconds? We got two numbers here in seconds, 1.84 times 10 to the negative 22 seconds, and we have 2.3 times 10 to the negative 23 seconds. So those are both seconds, right? So those both represent times. One of them is t, and one of them is t1 half. Which one's the half-life, t1 half? 2.3 or 1.8? Yeah, it's 2.3. The half-life of hydrogen-7 is 2.3. That's how much time it takes for half of the sample to decay. Why? Well, because each of these nuclei have a 50% chance of decaying, which means on average, half of them will decay after that amount of time. We have another number here, 27.0 grams. That's not time. So that's got to be either big N or big N0. Which one is it? Big N or is it big N0? Is it the initial amount or the final amount? Yeah, that's how much I start with, 27 grams. So we're going to call that N, and we're looking for big N. So we're going to call it N0, and we're looking for big N. Solving for big N, we got to use that second equation, right? N0 times 1/2 to the little n. N0 is 27.0 grams. But we don't know what little n is, right? That's easy, though, right? How am I going to find, Parker, how am I going to find a little n here? Good. T over T1 half. So that's going to be 1.84 times 10 to the negative 22 divided by 2.3 times 10 to the negative 23. And I believe when we do that, we end up getting 8. Little n is equal to 8. So sub that in back over here, and then plug it into your calculator. Now, we're going to do this as a group here just because we've never done a calculation like this before, in physics class at least, on our calculators. Look up here. 27 times 1/2, or let's just call it 0.5. This is not times 10 to the something. This is not second function times 10 to the something. There's no times 10 to the anything here. This is just (27) times 0.5 to the, I call it a hat. Okay, Mr. Royce, I think, calls it circumflex. That sounds pretty French to me. So we're gonna kind of combine the two. We're going to call it a chapeau. This is our little chapeau. 27 times 0.5 chapeau. Wheat. We end up getting 0.11. And the units for that would be grams. You can see here, after an incredibly short period of time, we end up with going from 27 grams to 0.11 grams. The reason that it decays so much in such a short period of time is because the half-life is so small. The upside to this, if there was ever radioactive hydrogen-7 nearby you, present, in Okotoks or in this room, the upside to that is that there wouldn't be very much left after a very short period of time, right? As long as you're not initially exposed to it, you could come back 2 minutes later and it would be essentially gone. It would be pretty much all decayed, right? The downside to it is, if you were present when it was decaying, when it was initially decaying, then it's a very, very high rate of decay. And you would almost certainly be poisoned, experience a high degree of radiation poisoning, probably lethal actually, depending upon the amount that you started with, because it's decaying so fast. Okay? So if you're there when this starts, watch out. But you only have to watch out for an incredibly short period of time, because then it's pretty much gone. Let's take a look at another example, then it's break time. The half-life of polonium-244 is 8 times 10 to the 7 years. How much time has passed before a kilogram goes to 62.5 grams? So let's write down some numbers here. We got 8 0.0 times 10 to the 7 years. Clearly, that's going to be a time, right? Is that t or is that t1 half? Yeah, that's the half-life t1 half. Good. How much time must pass? That's t, right? Right, Mateo? We're looking for the total time that's passed here. Before a 1 kilogram sample, that's an amount. Is that n or n0? Good. N0, that's what I start with. And the final amount is going to be 62.5 grams. Is it okay to use kilograms? Yeah. Is it okay to use grams? Yeah? What's not okay? Yeah, if they're different, right? You can't use different units here. So let's change that 1 kilogram to 1,000 grams. Could I have converted grams to kilograms instead? Sure. Doesn't make any difference there. I'd rather convert to grams than kilograms, just a preference thing. Okay, we want to find little t. The equation that we have that allows us to find little t is the one that's not on our data sheet. Little n is, I don't know what that is. T1 half is 8 times 10 to the 7, but okay, I don't know what little n is. So let's go to the other equation for that. Uh-oh. How do we find a little n? Good. How many people have used logarithms in math class? Some of you probably haven't. How many people have not used logarithms, have never heard of logarithms, or just don't like logarithms? Here's the first way to do this. The first way is using logarithms. We're going to say little n is equal to log n over n0 over log 1 half. So we're going to say log of n, 62.5, over 1,000, divided by log 0.5. Let's do that on the calculator now. 62.5 divided by 1,000. Now let's divide that by log of 0.5, and I get 4. So if I multiply 4 times the half-life being 8 times 10 to the 7 years, I end up getting 3.2 times 10 to the 8 years. Perfect. Right answer? Done. If you don't like that, if you're not comfortable with that, or you've never seen that, then use what I call the divide by 2 method, which gives you the same answer. The divide by 2 method involves creating a table. First column n, second column big N. We always start with 0, 1, and so on, as far as we need to go. After 0 ends, 0 half-lives, we've got 1,000 grams left. After 1 half-life, how much do we have left? 500. Good. Whoops, not 5,000. 500. After 2 half-lives, we've got 250 left. After 3 half-lives, it's 125. And after 4 half-lives, it's half of that is 62.5. So we're down to 62.5 in 4 half-lives. Either way you look at it, you get n, little n is equal to 4. Why can't you do the divide by 2 method in math class all the time? I mean, you could occasionally. It would occasionally work for you, but most times it's probably not. Yeah, exactly. This only works if it's a whole number. And the reason that that's going to work for us always in Physics 30 is because they tell us in Physics 30 that we don't need to use logarithms. That means that you get a question like this, it's got to end up being a whole number. It has to be. Because if you don't know logarithms, you have to keep dividing by 2, and the only way you're going to get an answer is if it's a whole number. One more question here that says example 2, it's really example 3. It says, using the graph below, determine the decay rate in counts per minute that the radioactive sample would experience after 3 half-lives. Whenever you see a radioactive decay curve, it will always take the form of n versus t. And the shape of it will always be an exponential decay graph like this. Now, on the y-axis of the graph that you have on your example number 3 here, it says counts per minute on the y-axis. That's an n, right? That's not a time. Okay, that's not minutes or seconds or hours or days. If it's not a time, it's got to be an amount. It's an amount of decays that are taking place per minute. So that's n. It could be kilograms, it could be grams, it could be percent on the y-axis. It could just be a number on the y-axis. Doesn't matter, it's always going to be n. And on the x-axis, you're always going to have t. Here's the bad news with these graphs. We can't easily straighten these graphs. And if we can't easily straighten them, we can't turn it into a y is equal to mx plus b graph easily, which means that we can't use the analysis that we've used on every other graph that we've done this year. That's the bad news. The good news is they don't expect us to go into any kind of detailed analysis of this. All they expect us to be able to do is read directly off of the graph one of two things: up and over, and or over and down. So you've got to go up and over on the graph, or you might need to go over and down on the graph, or you might need to go up and over and down on the graph. Let's take a look at this example to illustrate this. It says, using the graph below, determine the decay rate, counts per minute, the radioactive sample would experience in 3 half-lives, after 3 half-lives. Let's get the half-life first. In order to know what 3 half-lives is, we need to know what 1 half-life is. So we need to know what the half-life is. Let's figure out what the half-life is by going over and down. We start with 80 right here. After 1 half-life, we've got 40. So let's go over from 40 and go down. That takes us to 2. After 2 days, we have 40 counts per minute left. How do we know that? Well, because after 0 amount of time, we had 80 counts per minute. Or counts per days, I should say. So we go down to half of what we started with, over and down. The half-life is 2. Then what are we going to do? Well, what's 3 half-lives? If the half-life is 2, what's 3 half-lives? 6. So let's go over to 6 and go up and over from 6. We're going to find that the final amount after 3 half-lives is 10 counts per minute. And that's my final answer. So after 1 half-life, I've got 40 counts per minute. After 3 half-lives, I've got 10 counts per minute. I went over and down to find the half-life, and I went up and over to find the amount that remains after 3 half-lives. Make sense? Sometimes you're going to need to do both of those. That's as complicated as it gets. Sometimes it's half as complicated as that, because you just need to go over and down or up and over. All right, you can finish off what was assigned to you earlier. That was worksheet number 25, questions number 1 to 6.